The following is intended to be essentially an answer key to homework number 1, not necessarily a full answer key, but in such a way that if you follow it carefully, you will know what I was looking for in the problem set, and it'll help you in the future. Alright, so the first thing was you were supposed to write useful denials of the following words. F is an odd function or F is an onto function. Now, the typical useful denial of an OR statement is given by De Morgan's law, like so. Not P or Q is the same as not P and not Q. The only way that P or Q or both can be false is if both of them are false. Alright, so in this case, P is F is an odd function, so not P is that F is not an odd function, and not Q is that F is not an onto function. So the useful denial should read F is not an odd function and F is not an onto function. Now, a common mistake that people made is they said here that F is an even function is a denial of F being an odd function. And in fact, that's not true. There are many functions that are neither even nor odd. For instance, f of x equals x plus 1 is neither an even function nor an odd function. So even function is not a proper denial of odd function. Alright, so for part B, similarly, we have a similar version of De Morgan's law, namely not P and Q is the same as not P or not Q, like this. So, the denial of f prime of 1 is positive and f double prime of 1 is 0 should look like this. Either f prime of 1 is less than or equal to 0, right? That's a proper denial of f prime of 1 bigger than 0 because of the trichotomy of the ordering properties of the real numbers. So either f prime of 1 is less than or equal to 0, or f double prime of 1 is not equal to 0. Okay, let's move on to problem number 2. So here we have a hypothesis and conclusion. It's sometimes convenient to call one of them P and the other one Q. So here the hypothesis is P, which is that the sequence AN is convergent, and the conclusion is Q, that AN is a bounded sequence. Now, the useful denial of P implies Q is that P is true and Q is not false, and Q is false. In symbols it looks like this. You see, it's like that promise thing that I said in class, that by mathematical convention, for an implication to be false, it has to be that the premise is true and the conclusion is false. If the premise is false, then the statement is true for free. So in this case, that AN is convergent and it's not bounded is would be a useful denial. So that would be this. You see, it says the sequence AN is convergent but not bounded. Now I want you to notice this word but. That's sort of a stylistic thing. But is the same thing logically as and, but here it serves to mark the contrast inherent in an implication being false, right? So it's the same thing as saying that a sequence is convergent and not bounded, but it kind of highlights what's going wrong. Okay, so so this is a place where a lot of people made a mistake. So so some people thought that a useful denial would be not P implies Q. Some people thought that a useful denial would be P implies not Q, and so forth. So these are wrong. Really, a good way to deny P implies Q is P and not Q, and I suppose there are other ones, but that's probably the easiest one. Now the contrapositive of an implication is in fact an implication, and it's equivalent to the original implication. So the contrapositive of P implies Q is not Q implies not P, like this. So the contrapositive of this statement would be if the sequence AN is not bounded, then it doesn't converge. Alright, let's go on to number 3. So at first glance, this statement looks really weird, right? You have two totally false statements, 10 less than 3, 1 bigger than or equal to 2. Everyone knows those are both false. How does this proposition make sense? Well, the only way that it makes sense is in that way that I said on the last slide, which was that you know, an implication is true unless the premise is true and the conclusion is false. In this case, the premise is not true, and so the conclusion and so the implication itself has to be true. Now, as I said, a useful denial would look like this. 10 is less than 3, and the denial of 1 bigger than or equal to 2, which is that 1 is less than 2. And the useful denial is, of course, false, because, okay, it's true that 1 is less than 2, but 10 is definitely not less than 3, and the only way that an AND statement can be true is if both parts of it are true, and although this one's true, this one's false, so the useful denial in question is false. And it better be false, right? Because if a proposition is true, then the denial should be false, and vice versa, right? Some people made an error here saying that both the proposition and the denial were true, or that they were both false. And again, people made the same errors that they made in number 2 about what an actual denial of this if-then statement would look like. All right. Let's move on to problem number 4. All right, I've split this into 2 slides because you were supposed to do 4 things for each one. All right, so a well-written sentence. So the way I would write this might be for any natural number x. Note that I say any, not all. Again, that's a stylistic thing. You could say for all natural numbers x, but since you're talking about a particular one within the brackets, it makes sense to put it in singular here and say for any natural number x, if premise x is prime and x is not equal to 2, if x is prime and x is not equal to 2, then conclusion, x is odd. So as I've said again and again, the denial of an implication, well, we're actually not denying an implication, we're denying a for all statement and then an implication within it. So recall that a statement of the form for all x p of x, the denial of that is equivalent in a De Morgan type fashion, but not actually De Morgan's law, to there exists an x such that p of x is false, right? If it's not true that for all x p of x is true, then there must be some x for which p of x is false. So, and in this case, p of x is an implication, and so we're going to deny that. So a useful denial of the whole thing would be like this. There exists an x in n such that x is prime and x is not equal to 2, premise, and x is even. Denial of conclusion is the denial of the implication. Okay, so in words, that's basically what I said. There is a natural number x that is prime, not equal to 2, and even. However, that can't be true, right? Because, in fact, the original was true, right? If x is prime and it's not equal to 2, then it's odd, right? Every other even number is a non-trivial multiple of 2. All right, let's go on to part B. So this says there is some integer y such that for all integers x, x plus y is equal to x. So that's what it looks like. Okay, so for useful denial, we have to negate both the exists and the for all and turn them around. So it looks like this. For any integer y, there's an integer x, such that x plus y is not equal to x. There's no y that's neutral under addition for every x. Or you could say it like this. For any integer y, there's some integer x, such that x plus y is not equal to x. And again, I could say there exists some, but again, stylistically, you could also say there is some. It's the same. And again, the original is true because you could set y equal to 0. And that's all you need for an existence statement to be the case is if some element of your set makes it true, right? And it is true that if you let y equal to 0, yeah, that for any other integer x, x plus 0 is x. Okay, so for number 5, before writing the contrapositive, it makes sense to write the original in symbolic form, so I'll write it at the top. For all x, y, and r, if x is not equal to y, then f of x is not equal to f of y. So if you label the statements, P is the statement x equals y, and Q is the statement f of x equals f of y, then what you have here is not P implies not Q. So the contrapositive of that would just be simply Q implies P. Or if f of x is f of y, then x equals y. Which was how injectivity was explained to me in the first place. So again, our useful denial, we have to deny the for all and make it an exists, and then we have to deny the implication by having the premise true and the conclusion false. Right? And in words, that is, there exist real numbers x and y, such that f of x is f of y, but x does not equal y. All right? Well, and I hope you see why that's a denial of injectivity, right? Injectivity means that distinct things go to distinct values, and not injective means that there exists a distinct pair that goes to non-distinct values. Anyway, I hope that was helpful.